So today I would like to give you a brief introduction of Zener Diode, its function and application. We know that it is an essential component in modern electronics. So we'll discuss today about the Zener Diode and how Zener Diode can be operated as voltage regulator. Basically, in this lecture, we'll focus on following themes. First, we will discuss about the construction. Second, we will discuss about the working principle of Zener diode, and then we will go the characteristics that IV characteristics of Zener diode, and most importantly, we will cover in this lecture the voltage regulator, and we will also touch application, advantage, and limitation of the Zener diode. So basically, Zener diode is a very special type of semiconductor diode that allow to flow the current not only in forward direction but also reverse direction like a regular diode. Regular diode generally we get the current mostly or majority of the currents in the forward direction, and there are very less amount of current flow in the reverse direction. But in case of Zener diode, we can get the reverse direction current a lot. So only when the voltage exceeds a certain value known as Zener breakdown voltage. So that is the most important part of Zener diodes. So very first, the diode which operate in the reverse breakdown voltage with a sharp breakdown voltage is called the Zener diode. So it is a very special type of diode to design to operate only the breakdown region without damage. By adjusting the doping level during manufacturing or preparation of this material, it is possible to produce Zener diodes with a breakdown voltage ranging from 2 to 800 volt. That is a very broad range. So basically, the unique behavior makes the Zener diode incredibly useful, especially in voltage regulation. For example, that if we are designing a circuit and you need a constant voltage, suppose 5 volts, so regardless of any fluctuation of the input power, a Zener diode can used to clamp the voltage and protect sensitive component. So it works like this, that under normal reverse bias, Zener diode does not uh, conduct, but when voltage exceeds breakdown point, it suddenly allow to current flow, keeping the voltage across nearly constant. This control breakdown is sets the Zener diode apart. So Zener diode primarily depends for the working on Zener effect, and basically in the heavily doped diode the deflection region is very narrow. When the reverse bias voltage across the diode is increased, the electric field across the deflection region becomes very strong. When a field of this amount 3 into 10 power of 7 volt per meter, electrons are pulled out the covalent bond, a large number of electron hole pair thereby produced. This and reverse current sharply rises. This is called the Zener effect. So topically, the symbol of Zener diode is this. This side is positive and negative, this side. And what is commercially we see in the labs that looks like the Zener diode is this. So this mark actually is indicating that this side is the anode and this is the cathode. So one important to know that this very unique featured Zener diode invented by scientist Zener Clarence Melvin Zener in 1934. So Zener diode named after his name Zener, uh, and put as diode. So it is Zener diode. So we will often find Zener diode used in power supply, reference voltage circuit, surge photodetector, among others. They are inexpensive, reliable, easy to integrate, making them a go-to component for engineers. So it is a role in maintaining stability and protecting electronic circuit is truly powerful. Zener diode was, uh, as said, that was invented by scientist, the engineer Zener, and the specialty of the Zener diode is that it can operate in both forward and reverse bias direction. We'll have a look on working features and rating, construction and application. So remember to note the points that Zener diode is a special diode, enable current flow not only from positive terminal to negative terminal, that means that forward direction, but in opposite direction. The doping of the Zener diode is more than the conventional diode. So we have so called that it is the heavily doped diode, and the Zener diode generally normal diode is not operate in the reverse bias condition, but Zener diode is specially manufactured for the reverse biased operation. Zener diode is mostly used in types of electronic devices like computer, laptops, etc. It is the basic component of electronic circuits. It is used for power stabilizer circuit to maintain the voltage levels for a particular device. Zener diode also provides the protection to any of the circuit for over voltage, particularly from electrostatic discharge. So in electrostatic discharge, the current flows suddenly among two charge points by a short circuit or a breakdown of insulation. So let us first see that what is the principles of Zener diode. Its Zener diode works is a very unique features of breakdown mechanism. So what is the breakdown mechanism? This is basically Zener diode operates in the breakdown region utilizing the avalanche and Zener breakdown mechanism. So we will come details in following slides, that avalanche and Zener breakdown, and the voltage range. They typically function within the voltage range of uh, starting from 2 to up to 200 volt, depends on that which breakdown region is considering, avalanche or Zener. And most importantly, that these have the high current handling. That means Zener diodes are designed to safely handle high reverse current, making them robust for various applications. So as we seen that Zener diode breakdown is two different types. So let us see the details of this. So it is avalanche breakdown and Zener breakdown. So we'll first discuss about the avalanche breakdown. So what is avalanche breakdown? That this is just normal one PN junction uh, construction, P type and N type semiconductors, and we can see that here this side I have that majority of the electrons, and this side will be majority by holes, and negative terminal has connected with the positive and positive terminal connected with the negative, since we are connecting with the reverse bias condition. So basically this avalanche type of breakdown not only exists in Zener diode but also in general diode due to higher voltage in reverse bias conditions. When the diodes is in the reverse bias condition, actually the minority charge carrier get larger energy from the source and move fastly. So free electrons will hit the atoms at high speed and new electron hole pair is generated. So due to this large quantity of the electrons, the backward current will flow from cathode to anode. In some condition, the general diode can be damaged, but Zener diode may not burn because they sketch to operate under this condition. So the avalanche breakdown voltage of Zener diode is around 6 volt. So this basically is around 6 volt, and this is the typical avalanche breakdown diagram, or this is the features. So let us see what about the Zener breakdown. So basically that Zener breakdown, this is depicting the Zener breakdown. So we can see that one major difference in between avalanche and Zener breakdown is about the width of the deflection region. So basically in the Zener breakdown, it appears in high voltage like Zener, as this diode has less deflection region area due to the higher doping. So compared to avalanche breakdown, Zener breakdown have the doping is very high, and when the voltage applied to the diode increases, thin deflection area effectively established for electrical field is established, and when this reverse polarity voltage almost equal to the Zener voltage, the electric field in the deflection portion, this region, is strong that pulls out the electron from their valence shell. The outermost shell electrons that gets enough power from the field will break out from the effect of the mother cell. Means suppose this side have the field of holes and get enough power on the field that it will come out, that holes will be come out from the p side, and it will be come here. So the outermost shell electron breaks effect of its mother atom will move freely. So from here, from this side, there will be the majority of the electrons will move out, and from here the majority of the holes will be move out, and this region will be. So here this side is the positive ions, and here it becomes the negative ion. So due to the free drift of the electron, the reverse current will flow the diode. So it is actually connected in the reverse bias. Positive terminal is connected with the negative of the battery, and the N type is connected with the positive terminal of the battery. So this less increment of the voltage will cause to move current very fast at the Zener breakdown position. So there have the what are the basics comparison features of avalanche and the Zener diode. Let us look. First, the primary mechanism to work the Zener diode and avalanche. Zener diode generally works in the quantum tunneling of electrons. Avalanche, it is basically the impact ionization of atom by accelerated carriers. So these carriers basically the charge carriers. So this Zener breakdown occurs at low reverse voltage as compared with the avalanche diode, and it at high reverse voltage it is basically typically less than 5.6 volt, and avalanche is typically greater than 5.6 volt. So doping level of Zener diode is basically a heavily doped PN junction diode. Both are the PN junction diode, but for Zener diode the doping is heavily doped, and for avalanche breakdown it is lightly doped. Depletion region with for Zener diode is very narrow, as we seen. This is very important to differentiate, and relatively the avalanche breakdowns this depletion region with is relatively wide. Electric field strength very high due to narrow depletion layer, and for avalanche breakdown moderate but enough to accelerate the carriers. And another features about the temperature coefficient, that for Zener breakdown it is negative, and for avalanche breakdown it is positive. How it behave with the temperature. So basically the Zener breakdown, the breakdown voltage increases with temperature, and for avalanche breakdown this increases with the temperature. Zener diode it is decrease with temperature, and for avalanche it increases with the temperature. And mostly Zener diode is usually dominate when the voltage is required of about 5.6 volt less than, and for avalanche breakdown above when it is the very high voltage in reverse voltage that can be used for the avalanche breakdown. And now it is that what type of energy is involving. As we said that Zener breakdown is working in the quantum tunneling of the electrons. So here low energy electrons tunnel through the junction, and for avalanche, since it is the ionization of atom by accelerated carrier, so obviously here the high energy electron will collide and will create the pair. So device type is 3.3 volt Zener diode, and avalanche breakdown diode is 12 volt Zener diode. Generally, example means these are the means symbols to use. So if we short that, what are the primary difference between Zener and avalanche breakdown? Let us look in very compact way that in the Zener diode, the electrons tunnel through a narrow depletion layer occurs at lower voltage. In avalanche breakdown, the collision induced carrier multiplications happened at higher voltage. So basically now we'll see that what is the Zener diode in reverse bias. So how it connect in the circuit connection, Zener diode, how it connect in the reverse or forward bias. That the Zener diode in reverse bias, that if we connect, since Zener diode is a very special and bit sophisticated diode, so if we directly connect with this inputs, this is the input our source. So due to fluctuation it may damage the system. So if the input source voltage is very high compared to general voltage, so it may damage. So it is not preferable to connect in this way. So basically it's generally connected with this always that with the Zener diode in series with resistance to protect the diodes device. So generally in this way we used to connect in the Zener diode for reverse bias. So Zener effect actually exists in the reverse biasing. So what is Zener effect? Zener effect is the we can say that category of electric failure or breakdown that exist in reverse biasing PN junction diode. The strongly static field allow the electrons to move from the valence band to the conduction band of a semiconductor. So its name is due to the use of the factor in the operation of Zener diode. So this Zener diode is works in reverse bias under the Zener effect. So in short, it is basically the allowing the electrons to move from valence to conduction band of the semiconductor. So now let's see how Zener diode forward and reverse connection and how its characteristics is vary. So this is basically this diagram is basically the forward bias. So here we have the Zener diode. To measure its voltage we have connected a voltmeter and in series a ammeter for current, and here we have connected a series resistance, and this is connected with the rheostat variable resistance. And in the reverse bias is basically what we do, that just connect with the, here we connected basically the positive terminal of the Zener diode with the voltage or voltmeter positive forward bias, and in the reverse bias it will be opposite. The positive terminal of the diode will be connected to the negative terminal of the voltmeter. Here also same, the negative terminal of the negative terminal of the diode is connected with the negative terminal of the ammeter. Remaining is the same. So this is the typical IV characteristics of Zener diode. So basically Zener diode mostly works in the reverse biasing condition. So in the reverse bias the anode is connected with, as we seen that anode is connected with the negative terminal of the voltmeter and the cathode is connected with the positive terminal of the supply. In this given diagram, the reversing biasing effect of Zener is shown in this area in IV characteristics between the current and the voltage. So basically what happened when we provide the voltage to the Zener diode, a small amount of current as called the leakage current. This is basically called the leakage current. So suppose we are saying that this is leakage current, LE. So when the this leakage current flow in the diode till the point of applied voltage is less than the Zener diode. So this part we can see that current flow is very less. Okay. And next, when the value of the applied voltage approaches the Zener voltage, that means suppose here Vz, then a large amount of reverse current can flow in the diode. As we can see that this is the Zener diode, now current is flowing, and this part actually this part is the reverse current or reverse biasing current. So this part, this corresponding from where this current is very sharply increasing, this is called the Vz or Zener down voltage. So due to this instant increase of the current, the breakdown that happen in the diode is called the Zener breakdown. But Zener diode manifest a resistant breakdown that does harm the component, and the quality of Zener breakdown voltage fluctuates according to the doping level of the diode. Means it's fully that behavior and how much voltage tolerance can get in the Zener diode, it's fully depends on the manufacturing and how we are using the doping to the semiconductor material during preparation, it is hugely depends. So if the doping level is very high, then the level of the diode is larger, then the breakdown occurs at lesser voltage. If the doping is very less, the breakdowns happen at very high value of the reverse breakdown voltage. So this is also called the Zener voltage or breakdown voltage, and this current is called the Zener current. So usually, as we said, that this Zener voltage is typically from 2 volt to few volts, like 200 to maximum can go beyond 200, even sometimes it's 400 volts also. So yes, as we said that this is the main important part of the Zener diode, this reverse voltage and is current. So if we summarize the important points, that when we provide a voltage to the Zener, a small amount of leakage current flows in the diode till reach to the this region. So this is basically the leakage current, and we can see the forward bias is basically the normal PN junction diode characteristics. So when the value of this applied voltage approaches to Zener voltage, then a large amount of reverse current, we can see as we described, is flowing. So this suddenly, you can see that this suddenly it is changes to very vertical, this current amount. Next is, due to this instant increase of the current value, the breakdown that happens is called the Zener. So this region is basically the Zener breakdown region, and the voltage corresponding in the Zener breakdown region is called the Zener voltage. So this is the next. And next is that it manifests a still breakdown that does not harm the component. But generally normal diode, if we go increase the voltage use, it damages the diode. So the quantity of the Zener breakdown voltage fluctuates according to the doping level of the diode. So this doping level of the diode is a crucial role in this Zener diode operating system. And as we also mentioned, that doping level is larger than breakdown voltage, and it is less than it will be higher will be the this breakdown voltage than the supply. So conclusion is that doping is hugely uh, playing a crucial role, that whether and how it will behave and what will be the its breakdown voltage. So now will we move forward towards the voltage regulation. So first we need to know that why we need the voltage regulator. So generally, let us think that what happened when our mobile phone, we give the charging to get it charged, we plugged in, and or suppose your microcontroller, any of the receivers more voltage, then it is designed to means it's beyond its tolerance. What will happen? Any of the electronic device, whether it is your smartphone, laptop, any of the gadgets, or any of the small sensor in smart home system, basically need a constant and precious voltage to function properly, right? So if voltage goes too high, the component can get overheat, malfunctions, or even get permanently damaged. If voltage drops too low, the device might reset, behave very unpredictably, or fail to operate altogether, right? So that's where the voltage a voltage regulator is like the, you can say, the bodyguard of your circuit. It watch the incoming voltage and make sure only right amount can go through your device. So this is just, you can see that one, this is one AC input, and here we are going with a rectifier with a filter. So this is nothing but a diode, and we have added a filter here, and then we can get the DC output, and we can say okay, this is constant DC output, there is no problem at all. But if we have a like that variation of the AC input, like that fluctuation, and then if we add a rectifier with the filter, so what we will get? This DC output which we are getting here constant, we will not get it constant. It will fluctuate over this range. It will fluctuate. So it can increase way, or it will be in, or it can go in this way. So basically, that think that of your charger plugged into a wall socket, the power coming in is not always perfectly stable. So it might, due to the grid fluctuation, load change, or even noise from the other device without regulation. So these changes would hit your device directly, right? So inside most of the electronic circuits, especially in sensitive ones like microcontroller, communication systems, or in precision alarm component, the voltage regulation is not optional. It is very essential. In short, that voltage regulator needs, or it gives us the protect the electronic component from damage, ensure stable and reliable performance, extend the lifespan of a device, and handle fluctuation in input gratefully. So whether it's done with a simple Zener diode or more complicated circuit, integrated circuit, voltage regulation is one of the unsung heroes of modern electronics basically. So now if we suppose we have that input signal too much variation, and here we are getting to get the input output of your input signal, the rectifier with the filter we have added. And in addition to get the output, if we add a voltage regulator here, this we can say the modern electronics hero put here. So we can get over a broad area the constant DC output. So this will help you in many ways, like it will extend the lifespan of the device, it will handle the fluctuation, it will ensure the stable and reliable performance, and it will greatly help to uh, to protect from the fluctuation of the input power hugely. So today will we get this voltage regulator role of voltage regulators, Zener diode, that how can be implemented using many other components like Zener diode. So let us see that why we need to do the voltage regulation one more. That we know this is the transformer, input waveform, and rectifier low voltage AC supply, filters rectifying DC supply, and the regulator basically regulating the output DC. And we can see that irrespective of your type of input signals variation, we can get a regulated output waveform using the regulator. So now we'll see that Zener diode as a voltage regulator, how it work. This is very simple circuit, that this is the Zener diode, and it is connected with a input resistance, and here is our this V in, this is basically our input voltage, and output we are getting here, and we have connected with load RL. So the current which is flowing to the whole circuit is I, and current passing to the Zener diode is IZ, and IL is denoting the load current. So in voltage regulated power supply unit, the output voltage is constant and it is independent of the variation of input voltage and load resistance. So important is the output voltage is constant. It is independent of variation of input supply voltage and load resistance. So the unregulated DC applied across the diode through a series resistor. This is the series resistors R, which limits the input current. So main function of this input resistor is in this resistance R is the limit the input current. The value of these resistors is typically depends on that how much is your breakdown voltage. Initially diode operates in breakdown regions, and the P junction of the Zener diode is you can see that P junction is connected with the input voltage negative because it is in reverse bias, and the N junction is connected to the positive, so it is fulfilling the Zener diode is reverse bias. And this output voltage V naught is essentially controlled with the that how much whatever the input voltage we are giving, but it will be very constant and independent of the input, and this RL may vary with wide range depends on the need. So basically these are the components, or these are the basic features of the as a voltage regulator circuit connections. So we'll see that this is the circuit connection as we seen. So now we'll see that in voltage regulator how we formulated it. So basically in the Zener diode, that total current I, that is basically equal to the IZ, that is the current passing through the Zener diode, plus IL load current. And if we know that V is equal to IR by Ohm's law, so this V naught is that will be equal to IL multiply with the RL, or and also V naught, that is basically that what is we are giving the input voltage VI minus this IR. So we can write it as V naught is equal to VI minus IR. Let us suppose this our equation 1. This is our equation 2. And next we will get that V naught, which is nothing but equal to IL, that is the load current, IL into multiply with the RL. So this is our equation number 3. Now the variation of the output voltage may be due to two causes. One is the if load RL this is vary, or if the input voltage is vary. So if we vary the this in suppose we are vary the load current, then what will happen that the load resistance RL varies and input voltage VI remains constant. So if RL is varies, then we can write that RL is like arrow mark. That means it is variation and VI is constant. So output voltage V0 tends to remains constant. So from equation 2 we can get this delta I is 0 since Vi and R both are constant. So finally we can get from this equation 1 that basically delta I is delta Iz plus delta IL. So we can get the delta Iz, this basically minus of delta Iz. That means if we vary this Vi and R is the constant, then we can write is as delta I is equal to 0 because the voltage and R both are constant. So if we use this condition in equation 1, what we can get, the delta Iz is equal to delta IL. So thus if the load is increases, when the sharply voltage is fixed, load current IL decreases and the Zener diode current that Iz will be increased by equal amount. Thus the voltage V0 across the load will tend to remains constant. Now in next step, if we say that RL is constant and our input is varying, so we can get that from this equation, equation 2 again, the delta Vi is equal to R delta I. So we can write from equation 3rd that delta IL is equal to 0. That means delta I is equal to delta IL. Thus, the sharply voltage varies and the load current remains constant. The total current and I and the total Zener current Iz changes equally to keep the load current IL constant. Thus, if total current I is decreases, total current this I is decreases by delta I, diode current Iz will also be decreased by same amount. So load current IL this basically remains constant and voltage V0, this output voltage across the load will not tend to remain constant. So now we'll look that depends on this we can divide the regulator in different types. So basically the voltage regulator can be say as two types. One is the line regulation, another is the load regulation, depending on the variation of the load and the input voltage. So in the line regulation, basically the load resistance is constant as we said and the input voltage varies. In the load regulation, the input voltage is constant and the load resistance is varies. So now let's look the how we'll connect circuit connection in the line regulation and the load regulation. So basically this is a typical circuit connection of line regulation, that this is we are varying the voltage. So arrow mark in this voltage or in the resistance, that means that is the variable, means is varies. So this is the variation of load and sorry variation of the input voltage, and our load, we can say that this is the constant. So basically in the line regulation we can see that line regulation is basically refers the ability of voltage regulator in case of Zener diode. It's maintaining the constant output voltage even when the input supply voltage changes. So in simple term we can say that if the input voltage increases or decreases, does not does the output voltage stay stable? Yes. So how this line regulation works? It is 3 points to remember: that Zener diode connected to the reverse bias across the load. It maintains a constant voltage Vz across the load as long as the input voltage is above Vz and within the design operating voltage, and a series resistance R, or here we have given as Ri, is to drop the exit voltage and limit current. So it basically working condition is two, that V in this input voltage, that is this, we can say this Vs, it will be greater than the Vz. So we can say that Vs, that is greater than Vz. Zener diode conduct in reverse, clamps the voltage to Vz, and if Vs Vs less than Vz, Zener diode does not conduct, output voltage drops below regulation point. So main key equation or key formula for this R is V input maximum, means input voltage maximum, minus Vz divided by Iz plus IL. So where this V in max is the maximum input voltage, so basically we can define the R here as V input, or we can say that Vs maximum so this Vx maximum minus the Zener voltage, that is Vz, and divided by Iz, that is the Zener current plus the current flowing in the load, IL. So this VSM, this is indicating the input maximum input voltage expected. Vz is the Zener breakdown voltage. Iz is the Zener breakdown current, minimum Zener current for regulation, and IL basically the load current. So for the load regulation, so this is the load regulation circuit connection. We can see that what was our variation in the input source. Here this variation is in the load. In the load regulation, we are varying in the RL. So basically the load regulation, it is you can say that it is defined as the voltage regulator to maintain constant output voltage as load resistance changes while keeping the input voltage constant. Or we can say that if the load varies, more devices connected or disconnected, does the output voltage remain stable? So that is the fact, or that is the part what we do here. So in load regulation, basically that it is the same, that it first should be reverse bias connection with maintain the constant output voltage across the load. As the load resistance RL decreases, the load current increases, and voltage Zener compensates by reducing the own Zener current IZ, keeping the total current constant. And as long as Zener diode remains the breakdown region, the output voltage say that Vz. So basically here the main concept is first point is the total current I, that will be remains constant, Iz plus IL. As load current increases, Zener current decreases, or vice versa. So what formula we use for the load regulation? Load regulation is basically that total V load regulation basically will be divided as that V no load minus V no load, such as it can define as Vn, or V full load, that is Vf, divided by full load. And if we want to calculate as regulation percentage, then we will just multiply with the 100. So load regulation formula is given here, that it will be no load minus V full load whole divided by V full load multiply with the 100%. So this V no load, it is basically the output voltage when no load is connected, that is high resistance, and full load, that means output voltage maximum at load current, low resistance. And a good Zener regulator basically has a very small voltage variation, typically less than very less, it is less than 1%. So now the in line regulation, the load resistance is constant and input voltage is varies. If we summarized it, and Vi must be sufficiently large to turn the Zener diode on, to turn the, means input voltage must be sufficiently large to turn on the voltage, to turn on the Zener diode on. And for load regulation, input voltage is constant, load resistance is vary, and to small load resistance, therefore the Zener diode will be turned off. So this is, if we say as Zener diode is on, the load will be the off. Load regulation is the Zener diode off. So basically that if we get the Zener voltage, want to get the Zener voltage, suppose 5.1 volt, and our input voltage is 12 volt. Suppose input voltage is 12 volt, and load changes from 1 kilo ohm to 1000 ohm. So Zener diode current flow internally will be same, that output we can get that same voltage. Means suppose let me clear it, that suppose the Zener voltage V Z, this is equal to 5 volt, and our input voltage, that is V in, input voltage V in, that is basically suppose 12 volt, and our load is changes, that is RL is changes. Suppose it is RL is changing from basically changing from 1 kilo ohm to 100. It is varying. Okay, it is varies. So what will be the output voltage here? Obviously, the Zener adjusts the current flow internally, so output voltage will get this one only. So the voltage remains will be the 5 volt. Okay, so now let's see that what is the difference between Zener diode and the PN junction diode. So simple questions that can a PN junction be formed for a given breakdown voltage? Yes, it is possible to form the PN junction from a given breakdown voltage by choosing the doping. So yes, it can be formed for a given breakdown voltage by suitably adding the doping agent. This is the very crucial and very unique point for the Zener diode. And let's see that what are the general difference of the Zener diode over the normal diode. That ordinary diodes are operated in within the breakdown voltage in reverse bias condition. Operation beyond breakdown voltage may damage them. That means there is the damage of the system or damage of the diode. But in case of Zener diode, it is specially designed to operate beyond breakdown voltage. And this breakdown voltage we know already that it is basically the Zener breakdown potential or Zener breakdown voltage. And generally the normal diode is used for rectification and Zener diode is used for voltage regulation. So let us see that one Zener diode recitation that if a voltage supply is required to run a car stereo system from the car's 12 volt battery. A Zener diode with voltage of 9 volt and maximum power of 0.27 watt is used as voltage regulator. What will be the series resistance? If load resistance is 450 ohm, how will you find the diode current? So the circuit connection will be this, that as we said in the problems, that input battery we have of 12 volt and current suppose flowing the I, and Zener diode voltage is given Vz is equal to 9 volt and maximum power is given 0.27 watt. So here basically this I is the current drawn from the battery, Iz is the current through the Zener diode and IL is the current through the load resistance. And here it is mentioned that load resistance is 450 ohms. 450 ohms. So V output here is Vz only. So how we will find out the current? So actually the voltage drop across the this resistance R, this is equal to Vi minus Vz. So basically this R resistance voltage drop across R, that is basically the if we write it here like Vi minus VL is equal to V I minus V Z is equal to Vi is given 12 minus Vz is given 9. So it will be equal to 3 volt. Now we know that potential difference across RL, that is equal to VL equal to VZ. It is, so it will be 9 volt. So the load current IL, it is nothing but it is equal to the potential difference across RL, that is basically the 9 divided by the load resistance, that here it is given the 450. So this is basically equal to 0.02 ampere. So now the what will be the Zener current Iz? Zener current, we know the current drawn from the battery, that I is equal to Iz plus IL. That means Zener current plus load current. So here our load current is 0.02 amps, and our Zener current is basically, we have find out that the Zener current Z is, we have find out that Zener current, we find out the 0.02, and sorry, the load current IL is equal to, we have find out 0.02, and the Zener, this current Iz, this is basically equal to the, it is given the power, it is basically is equal to the P max, that is given 0.27 divided by the J max, that is the 9. So it is, will be basically, if we divide by 0.29 to 27 to 9, then it will be around 0.03 amps. So now the total current I, it will be basically IZ plus IL. So our Iz is here 0.02. If we sum this 0.02 plus 0.03 amps, this will be nothing but 0.05 amps. So the total value of the series resistance R. Now we can find out that voltage drop across R divided by the current through R. So the R will be finally, R value finally will be equal to voltage drop across R, that is the 3 volt we have calculated here, 3 divided by the current through the R, that is 0.05. So this is basically equal to, if we divide this, it will become around 50 ohm. So first we has to see that what is given in the problem. So in the problem it was given that input voltage Vi is equal to 12 volt battery, and we has connected with a Zener diode of voltage 9 volt and maximum power is 0.27 watt, and we have the load RL is 450 ohms. What is our series resistance, this R, and then find out the diode current I. So to find out the current I, we have to first find out the what is the value of R. So first the voltage drop across R, that will be nothing but Vi minus VL, that is equal to Vi minus Vz. So it is given 12 volt and Vz is given 9 volt, so it will be 3 volt. Now the load current IL, that is basically the potential difference across RL, so that is basically 9, and the load resistance, that is given 450. So our load current IL will be equal to 0.02 amps. And now if we want to find out the total current drawn by the battery, I is equal to current flowing through the diode Iz plus current in the load IL. So this will be nothing but 0.02 plus Iz. Iz will be nothing but, here the voltage is given and the power max is given. So Iz is equal to the, it will be the power, maximum power divided by the voltage 9. So we can get it 0.03 amps. So we can get at this 0.02 and 0.03, it will, we can find out around 0.05 amps. So finally the voltage value of the series resistor R, this will be nothing but, we have the this diode current, this I is 0.05, so it will be nothing but the voltage drop across R divided by the current through R. So 3 divided by 0.05 is equal to 60 ohms. So this is the Zener diode as a voltage regulator, and how to find out from a given diode, Zener diode values, that what are the total diode current and what are the variation of this. And now let us see that what is the main application of voltage regulator. So it first it is the stable output, next is the reverse bias, and third is the over voltage protector, over voltage protection. So Zener diode stabilize basically the output voltage. This happens under varying the input condition. They operate in the reverse bias breakdown region. This is the key for over voltage protection, and they are also valuable in small power supply units. So the key main circuit configuration to use as a voltage regulator are: first, registered Zener configuration. Second is, it should obey the Ohm's law, or accordingly Ohm's law it can run. And then is the stable output we can get from voltage regulation. So the features is, typically a set of includes input voltage, series resistance and Zener diode. Current limiting resistors involve the Ohm's law and power dissipation. The voltage output solely determined by Zener breakdown voltage. So there are various advantages of Zener diode as a voltage regulation. It is, first of all, it is high efficiency. Zener diode offers very high efficiency in low power circuit. Immediate response. Zener diode response is very immediate to voltage fluctuation. So it will be protect for the device protection. Cost effective, they are very compact. Cost effective solution for voltage stabilization. So despite all this, Zener diode has advantages, uses, and uses in many applications, in particular for voltage regulations. They have some limitations like limited current. Limited current handling typically less than 1 ampere. It also decrease the performance in high power applications, and also it have dissipations. Heat dissipation challenge at higher loads. So let us just see some practical applications visibly where we can use this voltage references. Use as voltage references in microcontrollers. In the microcontroller circuit, mainly use the Zener diode with the features of voltage referencing. It also uses an clamper circuit used in clamper circuits to protect sensitive components. And most importantly, it uses battery operated devices, critically in devices when need the constant output voltage. So these are the very important practical examples where we use the Zener diodes. So if we summarize it, that Zener diode basically gives critically that ensuring the stability are very essential for the voltage stability. Strength, they are strong in low power and precious application. So it is very important low power and precision applications, voltage stability and integral component. They are very integral to modern electronics for reliable operation. So I hope you will enjoy and you will understand the concepts of Zener diodes. So today is up to this. Thank you. Thank you to one and all. Thank you very much.